Hello, good morning, and welcome to the ITC tutorial session. This is based on week 1's quiz review, also known as the Death by Scrabble weekend. We had 2 takes, one on Saturday, the other on Sunday. As expected, the difficulty level on Saturday was higher. The objective of this session is to walk you through the thinking, the mindset, and some of the data that's come out of the weekend assessment of the entire batch. So let's start. So first, some data. Why did we do the quiz in the specific format that you've looked at? This is a plot of your skill set map that has come out of the 2 weekend assessments that we've just gone through. There are multiple things that we focused on when it came to assessment. The first was your ability to identify, document, and enumerate the problem space. I call this the counting problem. So given a choice of parameters or questions or variables or definitions, are you able to build a visual map in your head of that specific problem space? This is known as the enumeration, the problem space definition, or the counting challenge or a skill set. The second was your ability to abstract complex data. This is essentially judged and gauged based on giving you a piece of information that you have not seen before, that in most instances you're not familiar, and then expect you to, or ask you to, or give you time to reduce that piece of information or data set or requirement down to its essence and its abstract, and hence the term abstraction. The third was logical thinking, to your ability to look at a challenge and a problem, break it down using structured problem solving approach. So 3 specific parameters. There's a fourth one also, which is called pattern recognition, and I think on that most of you did reasonably well. This is the one, problem space, abstraction, and logical thinking, where we had the highest variation. So what does this plot show? This plot shows this is the person who had the highest score, this is the person who had the lowest score. What does the plot show? The plot shows how each candidate ranked on the 3 skill sets identified below: problem space, abstraction, logical thinking. It's based on the assessment data from the first quiz, the quiz taken on Saturday. Once we get data from the second quiz, the quiz taken on Sunday, this set would be a little bit more richer. But I think we have a fair sense of where the challenges lie. When you look at this data, where do you think the biggest problems are? If this is the highest score and this is the lowest score, you can clearly see that there is a significant gap in skill sets for the lowest scoring candidates in the pool. And the gap exists essentially at, if you'd say, if this is, let's say, 87, 85, you're exactly at the midway point. So about half the class has some elements of the requisite skill set, the other half is missing that. One of the reasons why we did the quiz in the way that we did it was to give both you and us a sense of where the weakest points are, so that we can focus on addressing and fixing them. Some of these challenges are simply a question of practice. So given a certain type of problem, if you look at it enough number of times, attempt variations of these problems multiple times, once you understand what the plan of attack should be, how should you approach them, how should you go about them, then it becomes easier, and the map, the assessment map that you see, will start filling in. The reason why we've done it this way is because we now have a picture and a snapshot of who you are at the start of the term, and we will get a sense of how this map evolves and changes once a month. Once we do that exercise once a month, we'll have a sense of whether there is progress being made or there is still a gap that is not being addressed. We can figure out how to address that, how to support that, how to cover it using supplementary sources and tools. So that's one. So that's the data part. Now let's look at the questions. What I've done is I've picked up one specific variation of the quiz that you went through. This is the quiz that we took on Sunday. The variation is VX. I'll speak a bit about that later. And then what I've done is I've taken the 11 questions in that variation that represent, to my mind, questions of a specific type under the 4 categories that we spoke about: abstraction, pattern recognition, logical thinking, and the ability to define a problem space. What we want to do is, when we see a question, we want to ask ourselves first. What we want to do is, as soon as we see a question, we want to first ask ourselves a very simple question. What type of a question is this? Is this an abstraction question, a problem space enumeration question, a logical thinking question, or a pattern recognition question? The reason for that is that your plan of attack for solving that problem, solving that question, solving that challenge is going to be based on the nature and type of that question. We also want to focus on what were the learning objectives of using that question as a basis, what skill did that question assess, and what was the difficulty level of that question. Because even though a question may be of specific type, its difficulty level may be significantly higher. We adjust that in the quiz by giving you more points versus less points. So simpler question, easier question, questions that require less effort only have a single point. Questions that are complex, questions that are difficult, questions that are heavy may actually have more points. So here's the variation that we're walking through. This is ITC T2 Q2 VX. If you took this variation, and I think we use this for 1, 2, 3 sections in ITC, and we used it for 2 sections in ICA. This was the hardest variation. If you scored low, if you got this variation and scored low, please remember that is not a representative score. The reason why we use this variation and you got it is because the groups that this variation was given to were groups that were identified as high profile, high potential candidates, and we wanted to see how you would react to harder set of problems. You heard of, tests. So when you take the GMAT or the GRE, there are computer adaptive tests that increase the level of sophistication, increase the level of difficulty of questions as you tend to do better with easier questions. Think of this as a weekend exercise where we actually did some adaptive testing based on the data that we got from you on the Saturday pass. And then using that data, the reason for giving you this harder test was to see how high could you test given hard level of questions. So on to the Death by Scrabble quiz weekend. So what I've done is I've picked up the easiest question first, and as we move forward, we'll get into questions with increasing difficulty. Think of it as a warm-up exercise where you want to sort of ease into solving the quiz. So the first question I picked up is the across the Spiderverse question, the animation question, the rendering question. This is a simple calculation question. So if you remember the plan of attack that you spoke about, what should be your plan of attack? This is clearly a calculation question. If you remember our plan of attack is, okay, what type of a question is this? This is a numerical question. What should be your plan of attack? You should build a simple calculation model, ideally in Excel or on sheet or on calculator or using paper. What's step number 1? Identify the relevant data. Step number 2, calculate it. Step number 3, test your model against choices. Step number 4, pick. So if we go back to the question itself, identify data. You are an animator working at Sony on the next Spiderverse film. The sequence has been created in animation of mixed frame rates. First part of the sequence is 24 frames per second. Lasts for 3 minutes. 3 minutes should essentially be about 180 seconds. But the second sequence goes down to 90 seconds at 16 frames per second. What is the total number of frames that need to be rendered out? So if you look at data perspective, you've got 2 pieces of information. One is 24 frames and you want to run this for about 180 seconds. So multiply these 2. And the second is you've got 16 frames and you're going to run this for about 90 seconds, multiply these 2. So both of these together should give you your total frames required for the sequence. But there's a second part of this question. That question is, if the render time for the first part of the sequence is 25 seconds per frame, remember this? So this is the first sequence and we have a second data point which is 25 seconds per frame, and the second part is 50 seconds per frame. So if you've got a second point here, 50 seconds per frame, what is the total render time in hours? So now if you think about this, your first step should be 24 into 180. This is 1, this is level 1, type 1, and then your second type should be 16 into 90. You get some answer. Let's say this answer is X, let's say this answer is Y. Your true answer is going to be the sum of X plus Y, but there's still some calculation that you have to do. You need to multiply this number X is going to be the total number of frames. Once we build the model, we'll figure that piece out. Your second challenge is that you need time in seconds. The time in seconds is going to be X into 25 and y into 50. So you get 25x plus 50y. What is this? This is the total amount you need rendering perspective so that you can get your answer in what? In seconds. So to convert that answer into minutes, we need to divide this by 60, and then to convert that answer into hours, we need to divide that by 60. Once you run through these calculations, you should be able to find an answer here. I have done these calculations in an Excel model because it's easier and faster to just do these calculations in Excel. Plus, Excel also gives you a record that you can use to cross-check your work, to validate your work, lower chance, lesser chance of making an error. If you're comfortable doing the same calculations in your head, feel free to do that. If you can use a calculator, do that. But I'd still recommend that whatever you do, make sure that you have a record either in Excel or on paper, because that'll help you review the answer and make sure that you've not made an error. So if I do the calculations, so if you go back to the sequence, we've done this, we have a plan of attack, we've identified the data, we've done the calculation. Now we need to test our model against the choices and then pick the right answer. I go back to my model, this model. What I've done is I've put this model in Excel just to save us some time, and this is what the model looks like. So this is my data, 180 seconds, 90 seconds. These are my frames per second, 24 frames, 16 frames, and my total frames then add up to about 4,320 frames for sequence 1, 1440 frames sequence 2, a total of 5,760 frames. So this is my first part of the answer. This is the total number of frames required. Then I multiply the frames by 25 and 50, which gives me about 100,000 frames here, 70,000 frames here. Total time in seconds is about 180 seconds. This gives me 3,000 minutes and 50 hours. Now the reason I've done this in Excel is sometimes you will see variation of the same questions. Sometimes you'll see questions that ask you different pieces of the puzzle. If you build the model, then you build the model once and you can use the same model multiple times so that you can go out and answer the same question by doing the work you performed while doing the base calculations for question number 1. If you see a second question in the same space with similar variation, then it's just a simple question of extending. Sometimes you see variations that all you need to do is, if the model is built, you just need to move or tweak some of the data elements and you get your answer. So in this specific question, the answer we want, the first part is number of frames, which is A, 5760, and the second part is time in hours, which is about 50 hours, which is B. So what is the right answer? If I go back, the right answer is 50 hours. There you go. This is the right one. Is this correct? 5760. If we go to the answer is 576. There we go. So 5760 and 50 hours. The correct answer in this specific question was B. 5760, time in number of frames, and oh sorry, this should be time in hours. My bad. This should be time in hours. Okay. Alright, so 50 hours. Next question. Our next question is a algorithmic thinking question. How do we know this? Consider the following sequence of steps written as part of an algorithm. Now, remember, this is not code. This is a thinking question. We're not writing code. We're not asking to write code. We're simply asking you to look through a sequence of steps. So if you see variations of these questions, the only objective of these questions is to help you think. If you don't want to think of this as code, don't think of it as code. Think of this as a simple mathematical sequence of instructions that you have to follow to solve a problem. So now, let's apply our approach. Let's identify. What type of a question is this? This is a logical thinking question. What should be a model? Our model should be tracing all the steps that have been asked to trace. What is our first step? Identify what is changing. What is our second step? Do or trace both plot and a model. Step number 3, test the model against choices. Step number 4, pick your answers. So in this specific instance, if we go back to the question, let's identify what is changing. So move 1, this is the number 1, to the variable sum. So we've got a variable here called sum. I need to trace and track this. Move to the variable counter. I have a second variable that is called counter. So I need to track and trace this. That's 2. Then add counter to sum, that's an operation. Add 2 to counter, evaluate if counter is greater than 9. If yes, print sum, and end if counter is less than 9, go to step 3. So I think the right model for solving this should be that we do a sequence. So when we start the program at time 0, what is the value of sum? The value of sum at time 0 is, move 1. At step 1 is move 1 to variable sum. So we move 1 here. Then move 2 to variable counter. So add 2 to counter. Alright. So that's 2. That's step 1. Then add counter to sum. So now I've added counter to sum. We're still here. So now once we add counter to sum, in this specific case, this becomes, what is the value of sum? The value of sum while we're still in time 0 becomes 3. Then what do? Then we do add 2 to counter. So now we've moved this here and then we added 2 to counter. So what does the value of counter becomes? It becomes 2 plus 2. So counter is now equals to 4. And then evaluate if counter is greater than 9. No, counter is equal to 4, so it's not going to change. So now if you see here, this was 1 and this was 2. That's what we were adding. So we now go back to the next step, which is if counter is less than equal to 9, go to step 3. Step 3 is where? Step 3 is here. Okay, so now we've gotten the second run of this. In this second run, what are the starting values? Sum is equal to 3, counter is equal to 4. What do we do? Add counter to sum. Add counter to sum. So what do we add to sum? We add 3 plus 4 to counter. So now sum becomes 7. Then we add 2 to counter. Counter becomes 6. And then we apply the condition. So now over here it might be useful to just test. Put a tracker for, let's say, a flag or a test and track the test. So is counter greater than 9? Counter is equal to 6? No. So this is not true. This is false. And if counter is not great, if yes, print sum and end. If counter is less than 9, go to step number 3. So we again go to step number 3. And now where are we? Now we're in the second run. The second run, we've got this variable called sum. We've got this variable called counter, and we've got this flag. We want to trace those. So we start with 176. What is step number 3? Add counter to sum. What is the value of counter? 6. What is the value of sum? So sum becomes 13. And what do we do next? Add 2 to counter. Counter becomes 8. What's the value of the flag? Is counter greater than 9? No, it is not. So this is still false. And if it is not, then what do? If counter is less than equal to 9, go to step number 3. This is step number 3. Step number 3 is this is step number 3 here. So we now on the third loop, in a third loop, counter to sum. Add counter to sum. Sum is at 13, counter is at 8, we add the 2, we get 21, and then what's the next step? Add 2 to counter. Counter is now 10. Apply the test. Is counter greater than 9? Yes, counter is greater than 9. If yes, print sum and end. So 21, and here this becomes true, right? So you ran 1, 2, 3, 4. So 4 versions, and that's where you sort of finished and exit the loop. Now the question is, what is the printed output for this program when it ends? What is supposed to print? It's supposed to print sum. What is the value of sum? 21. Is 21 here? 21 is here. There we go. The correct answer for question number 7 is 21A. That's the choice. So you now think about what you've just done. You've built this model, a trace, a plot, where you simply tracked what was it that changing. Sum was changing, counter was changing, and flag was changing. 3 things were changing: sum, counter, and flag. And what you've done is you've basically tracked those 3 across the program as it walks through. Now when I say program, I'm being generous. It's essentially a set of mathematical instructions. You've got a couple of variables, same variables that you see, that you're comfortable with, that you've dealt with earlier in your life when you dealt with algebra, when you did calculus, when you did trigonometry. So same variables. What you're really trying to do is you're trying to trace and track how those elements change as you move through the execution of your algorithmic loop. Hence the term algorithmic thinking. Can you think and trace an algorithm either on paper or an Excel sheet or in your head? Right now what you've done is I've used the slide as my sheet of paper. You can do the same thing in Excel, in a Word document, on paper if you prefer. And if you are able to, though I would not recommend that you should do that, you can also trace and track it in your head. The problem with doing all of this in your head generally is that right now these are very simple questions. As you start looking up at more complex, more advanced problem sets, it's going to be difficult to track everything that is changing in your head. So I'd recommend, I think two recommendations. One recommendation is, even though I said and I told you that you should, and that you can be able to take this in a car or on a bus, my recommendation though is don't do that. My recommendation is find a quiet place or a quiet corner. Make sure that you will not be disturbed. Make sure that you attempt this on a laptop, not on a cell phone. Make sure that you have paper that you can use to sort of write things down, because sometimes writing things down is faster on paper. Sometimes writing things down, typing things down into laptop is faster. But I think all of us have a different sequence, different preference, different way of thinking. And the best possible bet that you should take, that you should be able to do, is to essentially try and see if you can use whatever tool you find it faster to work with. If it's the laptop, use the laptop. If it's the phone, and there are people who prefer the phone over the laptop, use the phone. If you prefer paper, use paper. But make sure that you are in a place, in a location where you're not disturbed, you're not distracted, and that you can devote your entire bandwidth, your mind, to solving and tackling these problems. All right. So we've done question number 7. Question number 7 was an algorithmic thinking question. Next question. Question number 7 was an algorithmic thinking question. We went through this plan of attack. We built this model on our slide, and here's a cleaner, nicer representation of the same flag. So if you see this, this is the same. This is the sequence. This is sum. This is counter. This is the flag. Not true, not true, not true, not true, and then it's true. The answer that it prints is 21. This sequence is not so much in terms of loop, but I think more in terms of how variables are changing, and you've seen the results that we've calculated so far. The next question is also an algorithmic thinking question, but there is a slight change, and the change is we're not asking for you to print the value of sum, we're asking you to print and tell us the value of counter. Go through our plan of attack. Our plan of attack is, what type of question is this? This is a logical thinking question. Trace steps, identify what is changing, trace plot and models, test model against choices, and pick the right answer. But we've just built the model. We built the model in the prior section, and the prior section is here. So what is the value of counter when the tool exits? It's about 10. Is that the question? Yes. What is the value of counter when the code ends and prints the value of sum? The correct answer once again is A, which is the value 10. So now you see a change. If you put in the effort to do it correctly in Excel, the variations is not that hard because you already solved it. And because you were tracking it, it was possible for you to simply look up the question like with the snap of a finger. And because you built the model, you had all the data, all the calculations available. It was very, very simple, very, very easy for you to pick the answer just like this with the snap of your fingers. So sometimes building the model could be very, very useful because you don't know what's coming up next in the question. There are going to be some variations later on in this course where you will not just be tested on your ability to recognize a question and pick up the right plan of attack. You would also be tested on how smartly, how sharply you use your head to attack the quiz. All right, next question. This was question number 8. So we've done two algorithmic questions. So we've done two algorithmic thinking questions. Let's move on to the next question. Next question is our death by Scrabble question. These are my favorite type of questions. You'll see a lot of these, not just last week, but throughout this course as you move forward. And the reason for this approach, there is certainly a plan behind my madness. But first, let's see what should be a plan of attack. So here's our assessment funnel. What type of a question is this? This is a counting and problem space question. What should be our plan of attack? We should count. How do we count? We generate variations, then we count in total, then we validate and review, and then we pick our answer. So if I go back to the question, what is the question asking for? Consider the Scrabble board and the tiles available to you on your slate. This is the board, these are the tiles. What is the sum, focus on words, sum of the tile scores of all the valid words within the Scrabble dictionary that can be generated from the slate that include the letter W? So these two, right? Now what words can we generate? So immediately the first two that come to my mind, one is wow, one is low. So W-O-W, wow, and then W-O-L, that is W-L, but if I reverse this as L-O-W, that's low. Then I also have W-O-O-L, which is wool. So that's 3, so that's 1, 2, 3. What else? How many other words can you come up with that use some combination of W, O, O, T, W, L, and U? So I have in the Scrabble dictionary there is another word that's called woo. You can validate and check it. So I've got wow, I've got low, I've got wool, I've got woo. I'm not sure whether ow is a valid word. You can look it up and see whether it works or not. Then you also have two. There you go. There's two. So you've got these words, right? Now, if you have these words, how do you process them? How do you move forward? So a W is worth 4. So the score would be 4 plus 1 plus 4. Low would be L is 1. O is 1, low would be 1 plus 1 plus 4, wool would be 4 plus 1 plus 1 plus 1, woo would be 4 plus 1. You get the sense, you get the sequence. So what is the sum of all the valid words within the Scrabble dictionary? You've got the words, you've generated the words, you calculate the words, you sum up the words, you add them up. In this specific case, I'm actually not going to tell you the answer. You should be able to do this calculation by yourself, but I'm happy to show you and share the model I have. So there you go. That's wool, wow. Oh, we missed out owl, and then there's low, and then there is woo, right? These are some of the words. There could possibly be more words. In this specific question, you can actually see variation. So if you think about this, this is Scrabble. What is the value of the highest scoring word that has the letter W in it? What is the highest scoring word placed for a word on this board that includes it? These are both valid variations. Now, if you think in terms of the first question, which is the highest scoring word that has a letter W in it, that would, by this sequence, that actually be wow. And if you think in terms of what is the highest scoring word placed for a word on this board, which includes a letter word W, placement is important. So Scrabble is not just a game that deals with generating words. It is also a game that focuses on strategy. And the objective of the game is to, if you think in terms of, if you play with the AI and you focus on what the AI does, you can actually see how the AI is playing the game in such a fashion. Think of Scrabble not just as a word game. Think of Scrabble as a game of chess. But rather than using pawns, you are using words. The objective of the game and the key to winning the game is make sure that these double word bonus, triple word bonuses are not opened up earlier on, are not opened up in such a fashion that the AI can take advantage of these. So you want to sort of deny your competitor, your opponent, access to these words, and then you want to maximize access to it. So these are one. The other variations are these, the triple letter words. So this is double word. This will double the word. This will triple the word. This will triple the letter, the score on there. So if you put W here, it won't score 4, it'll score 12. If you do wow, wow would be, let's say, wow is going to be, where's wow? Wow is 9. If you manage to get a wow on a triple word score, your score would be 27. So what's the plan of attack? The plan of attack is enumerate the words, then add them up, and then try and figure out if that model works for you. So what is the plan of attack? It's a problem space question, enumeration question. Enumerate the space and generate the choices, and then go back, add them up, and see what the true correct answer should be. As I said earlier, this I've shown you how to do it. So I've solved the first 3 or 4 questions for you. I've shown you how to do this. I want you to try and solve it on your own and seeing what kind of answers you get. That's the approach that you should take. So the next question. Next question is also from the Death by Scrabble question set, and this is a question that asks for the highest board score after optimal placement on the board. So you've generated the words. Remember the words that you've done previously? You've generated those words. You have a sense of what the scores, and now you have to think in terms of how do you place it. And I think there are multiple ways of answering this question. There are multiple variations and combinations of generating these pieces. Why did we ask these questions? One of the key things that we're doing as far as this course is concerned, the IDC course is concerned, we're using Scrabble as your mental gym. Given the variations, given the rich set of possible scenarios that are likely, given the huge permutations and combinations that exist in the problem definition of a game of Scrabble, we want you to think as widely as possible. If you remember, I've insisted, I've emphasized, I've repeated this again and again. The objective of computational thinking is to help you think and see stuff that we normally don't see. The objective of computational thinking, as far as we're concerned, is to help you count. Count, why? Because without counting properly, in most instances, you will not be able to see boundary condition. You will not be able to think at intersection. You will not be able to identify areas that people normally miss because they are not committed and dedicated enough to explore the entire problem space. And as part of that problem enumeration, as part of that counting, sequencing exercise, it is important for you to list down and generate all possibilities. Scrabble provides this in a very simplistic, natural, and fun fashion. Fun fashion as long as you're not taking quiz. As long as you're playing the game, you're having a lot of fun. But even if you are not playing the game, and even if you're taking the quiz, remember, it's an enumeration question. So if I go back to my plan of attack, counting and problem space, count, generate variations, count and total, review and validate, and then pick answers. Unlike the first question where you're generating word variation, in this specific instance, you have to figure out where. So you already have a list of words. For example, I have wow. Where can I place wow? So I can place wow here. So I can do wow here. So if I do wow here, that's 4 and 4, that's 8 plus 1. This will give me 9. So that's, I have one answer. Okay. Now I can also do 2. So if I do 2 here, this is W here and O here. So I get W here and O here, right? So I've got 1 and I've got 2 and then I've got 4, that's 6. And this is a double word score, so I get 12. So if I do 2 here, I get 12. What else can I do? Do you see? So you've done wow, you've done this. You could also do low here, so you can replace this and you can just do low. If you do low here, is your score going to go up or go down? It's not going to move. It's not going to go up. It's going to come down because low is just L is just 1. So it's 1, 2, and 4. It'll be 6 if you do low here. But you could also do low here. So you could do low here, low, and then W. And what this would do is, because you're doing low here, this L, which is 1, 2, 3, 4, 5, you get these 5, then you get 5, 6 and 4. 6 and 4 is how much? No, sorry, I did this wrong. So you get 1, 2, 3, 4, 5, that's 5 from this side, and then low, you get 1 and 2, that is, and then 4, that's 6 on this side, so that's 11. So 17. You've done some of these variations and you've seen where that takes you, and here's what the answer looks like. Here's the solution. Now in this specific case, the correct answer is low, and that adds up to a total of 17. How do we get to 17? Remember, this piece right behind this O is a double word score. So if you take low, which is 1, 2, and 4, that's 6. 6 into 2 gives you 12 because you double worded. And then 1, 2, 3, 4, 5. This is a bonus that you get because you added lions. So this entire word becomes part of your score. That becomes 12 plus 5, and that gets you to 17. So the correct choice from our perspective is, if you go back to choices, answer is A again. 17. 17 is the correct answer. Next question. Our next question is the question that everybody hates. This came from, I think, the most hated article ever prescribed for pre and post reading in a course. This was the comparison of the E. coli genome with Linux call functions. I've already explained to you in the class why I felt this was a really important piece of reading. I think the reading is really core to the essence of not just competition thinking, but values that you should focus on. Context and debate, this is really important for somebody who wants to spend time in the field of computer science. I know it's a very hard article. I know a lot of you don't have background and context in the field, but there is a reason for this. And the reason for this is essentially the nature of this specific question. If you take a look at your evaluation sheet, the Linux versus E. coli genome comparison questions. These were questions that were prescribed from the reading on a comparison of E. coli genome and its evolution, and compared that to Linux call function. The paper in this specific question specifically focused on comparing nature as a programmer against humans. And the two benchmarks it used was the evolution of the E. coli bacterium and its genome over the last couple of 100 million years, and compared that to the evolution of Linux call function. It's a great article, highly recommended. I know it's hard to get, hard to understand, hard to digest, but you get there. You will ultimately get there. Now, why was this article prescribed? Remember abstraction? What is abstraction? Abstraction is your ability to take a look at something you've never seen before and drill it down to its essence. So the nature of this question is an abstraction question. What do we need? We need a truth table. Now, you can't build a truth table if you haven't read the article, and I think one of the reasons why we've assessed this question in this specific fashion is because we want to introduce you to the concept of a truth table. Truth table is a set of truths that you can use to simplify, to drill down, to easily access the essence of your reading, your learning, or your requirement document. Step number 1, review the truth table. Step number 2, cross-check assumption, data and results. Step number 3, validate and review. Step number 4, pick answers. So what does a truth table look like? You remember this? We'd build this truth table, we'd share this truth table in the class, and that table compared the difference between science, art, and design across a range of pieces. Where did this came from? This came from the required, prescribed, recommended reading article on engineering, on design is neither science, art, nor engineering. Right? What would a truth table for the E. coli versus Linux comparison look like? You want to take a look? There we go. So that's what I built. You've seen variations of this over the last 2 days in multiple test questions when we looked at comparing the E. coli versus Linux article. But to do and to ask those questions, this is what I had to do. So I read the paper and I made the table, and then I tested you on the table. If you'd build the table, if you'd build the truth table, the question would have faced you. And if you think in terms of what is the essence, the article makes a number of points, but there are 3 or 4 core themes. One of the themes is comparing E. coli with Linux. One of the themes is how does E. coli versus Linux differ specifically in terms of how hierarchy and functions change and behave when you compare E. coli with Linux operating system. And that hierarchy essentially is 3 key drivers. One is what Linux and E. coli call the master regulator, both in terms of genes and functions. One is what we call the manager function, both in terms of Linux and E. coli. And one is what we call the workhorse function. And then these are specific truths with respect to the relationship between these drivers and functions with reference to the article question. And here's a summary of how they differ. So how does the master regulator, the manager, and the workhorse differ from each other, right? This is my truth table. Now, If I go to the question itself, what does the question ask? Come back. Question asks me a very simple question. In what fundamental way does the layout of the E. coli transcriptional regulatory network differ from the Linux call graph? Right? There's a picture of the call graph here, picture of the Linux piece here. Now there are 4 statements. What we need to find out is which one of these is true. So E. coli's network has a greater number of master regulators. Is that true? Relative to the proportional representation of such genes within the Linux network. So we're not sure. Put a question mark here. Linux network is characterized with distinct modules, while E. coli network has blurry boundaries between functions. So this is clearly not true because distinct boundaries here, distinct boundaries here, right? So this is certainly not true. So we cancel this out. E. coli's network is more prone to errors and has crashed in the past due to its complex specialized structure. This we also know is not true. If you remember the article, covers the article actually talks about the fact that E. coli is actually a lot more robust and stable because that's what nature solves for. Linux network consists mainly of master regulators, while E. coli's network relies on workhorse genes. Workhorse genes, master regulator. And if you look at this could be a possibility. Yes, this is true, and E. coli is on workhorse, and these are the workhorse genes. So this could be possible. So the correct answer would be between D and A. E. coli's network has a greater number of master regulators relative to the proportional representation of such genes within Linux network. That does not seem to be true, because so the trick here, the challenge here is this word, right? To the proportional representation of such genes within the Linux network. So I would leave this to you. I don't have the article right in front of me. I haven't looked at it since I put these questions together. I would recommend that you go through this. You've understood that this is not true. This is not true. The right answer is somewhere between here. My guess right now would be that this is most likely not true, but I am not sure. I think this is possibly not true, but I would still need to refer to the relevant piece in the article to find out what the right answer is. You can go ahead and do that for me. So that's question number 4. Next question is question number 5. Also from the Linux OS versus E. coli bacterium. Question said, what is the question? When comparing nature and human programmers with reference to Linux and E. coli call graphs, which of the following statement is and are true? Stability and robustness in systems thinking is directly proportional to the frequency of changes in the system. This sounds okay. Linux is a better platform in terms of stability than E. coli because it is all faster and change more. This is most likely not true given what I remember of the article. Nature is a slower and more careful programmer than human systems because nature doesn't limit change to just necessary insight. This is a really tricky statement. This is true. Nature is slower and more careful programmer. Yes. Then human systems. Yes. Because nature doesn't limit change to just necessary. This is not true. If you read the article, you will find there are multiple references that make the same point that this is not true. Nature actually does limit changes to just necessary and sufficient. Both the E. coli network and the Linux graph exhibit hierarchical layout, but their functional requirements remarkably similar. No, they're not. Despite their different origin, they are not similar. So this is also not true. This is not true. This is not true, which basically means that the only answer that's left is A. And the reason I put this question in, the reason why I'm covering this in the tutorial, the reason why we allocated this article, and this is the theme, this is the central reason for making you read the E. coli versus Linux comparison, is you will build many systems later on in your life. And the stability and robustness in those systems is going to be directly proportional to the frequency of changes in that system. So be careful with respect to changes. Anytime you make a change in a running live platform, there's a reasonable chance that something will break. And not because you're a bad programmer, not because you've done something wrong, not because you've not followed the process, the sequence and chain. That's just how things work. So stability and robustness in systems thinking is directly proportional to the frequency of changes in the system. I know you hate this article. I know you hated every time you saw questions that came from this set in front of you over the last 2 days. But I hope that given that trauma, given that experience, given that process of thinking that you've gone through, you'd remember these 2 lessons. One, is stability and robustness in systems thinking is directly proportional to the frequency changes in the system. One here. And in the prior question, this one here, Linux network consists, where was it? This one, right? This was it, right? Linux network consists of master regulator, equalizer network consists of. Next question. The next question is also from the same set, Linux versus equali comparison. And this actually requires you to refer to the truth table. In the attached visual map referencing the comparison of workhorse nodes across equal and Linux call graph, which of the following references are true? 1 below refers to the first line marked in the attached map, so this is 1. 2 below refers to the second line, which is 2. 3 refers to the third line marked in the, which is 3. Only 1 is true, only 2 is true, none of the 3 are true, both 1, 2 and 3 are true. Okay, so we have the truth table. There you go, that's the truth table. Compare this to this and you should be able to answer the question. The trick here was not to build the truth table at runtime. The trick here was to build the truth table as you read the article. And if you remember I think in one of the class when I'd asked you about how you read the article and you made a statement, I said, that's not how you're supposed to read it. You're supposed to read it so you can understand it and build an internal representation of the essence of that article. If you'd build that internal representation, this is what it would look like. If you had that ready reference, you should be able to answer this question. So I'm not going to answer this for you here. You can go to the truth table yourself and figure out how to answer this question, because everything you need to answer it is now in front of you. Next question. Next question is again death by Scrabble. And so if you've gone through the earlier sequence, this is the same question again. This is, what is the sum of all 3-letter words that you can make that include the letter P? So enumerate all the letters with P. And using this slate, so for example, my first choice would be pun and then pin, but there is a then pain, and so P-A-I-N, pain, and then P-U-E. Then also I don't have, I don't have E, otherwise I would have done pain, but I can find E on the board. But again, there you go, that's pan, so that's another word. So pun, pan, pin, pain doesn't apply. This pain doesn't apply. Why? Because you're looking at 3. So again, what is the type of the question? This question is a counting and problem space question. What do? You count, you generate variations, you count and total, validate and review, pick the answer. In this specific case, generate all variations of P, and then what do? Then you sum them. And then you sum them. What is the sum of x? The sum of x is an answer between these 4 values. I'm not going to solve this question for you. Just showed you how to do this. You can go ahead and attempt it yourself. It's also up and running in the problem set test bank that you have access to. That access will remain valid for the next 24 to 48 hours, so that you can go ahead and practice question again and see whether you get this right or wrong. All right. Next question. The last question is also from Scrabble. This one is highest possible score is X, which of the following statement is true. Highest board score for optimal placement. How does this work? This should be, there you go. So do we have a highest board placement? Oh, this was the pin one. This was the pin one. No. So I don't have a solution here for this one. So make a list of all the words that come with P. So in this specific case, it's going to be, so it's pin, pack, snap, nip, pun, and pox. If I look at placements, you've got multiple choices. You've got P, so I've got P and I. I could do dip, so D-I-P. But dip is going to be 2, and then there's double letter which is for I, so that's 2, that's 4, and 3, 7, so that would give me 7 for dip. I could do I could do pine. Pine would be P-I-N-E, so this would be 3 and 1, which is 4, and 1 which is 5, and 1 which is 6 for 6 here. So multiple variations. I could also do So I could do kip. Kip is a valid word, and I've got x here, so I do x here. Pax is also a valid word, so I'd get 5 plus 1 plus 3, so that's 8. But then I get a double for p, so it's going to be 5 plus 1, that's 6 plus 6, so that's 12. And then I do pax, so then I get another 3, and then 1, which is 4, and then x is 8, so 8 plus 8 is 16, so 16 plus 1 would be 17, and 3 would be 20, and then double for the p, so that's 23 plus 12 is 35. If I do kip plus pax, so this and that should give me about 35. So if I go back to my choices are, so somewhere around here, certainly not here, not here, and not here. So this one, most likely this one. Not sure, again, you can do the math and run the numbers yourself and see what the correct answer is. So this covers this one, and then the third one, the final question from the Death by Scrabble set is, consider the Scrabble board and tiles available to you on your slate as shown in the shared image for this question. Strategically, why the choice of placing the word basic on the board is not the best of all possible choices. This I can tell you very, very easily. The objective of the game is to deny your competition access to the board. By putting up basic, I'm clearly opening up one triple letter word, literally serving it up on a platter for them to take it on. I'm also opening up sequences here, and this is far away, this is far enough, but I've opened this one and this one, two triple letter word, and then a sequence of these words. So I think that is the correct answer. But if I see the choices here, the word score on the board is only 10, and the better placement of the same word on the board is possible. Maybe, I don't know, I'm not sure, I have to check that. There is not enough information to answer. No, this is not true. It misses a triple word score bonus. Yes, this could possibly be true. It opens up the board for the competing game. This is the most important reason. So given a choice of choices, two of them make sense, but I think the fourth one, the final one, is the one which is the most important, the most valuable. So by this time, I think you've gotten to a point where you're doing this automatically. You don't have to think about this. You don't have to think about the type. You see the type, you know what you have to do. You go ahead and do what needs to be done, and then you execute on the full sequence. It's just a question of practice. With a lot of these questions, a lot of this assessment, the primary objective is for you to help use these specific type of muscles in your brain so that you can start to think along these lines. Once again, let's go back to the discussion on how do we teach computational thinking? Why do we teach computational thinking? The whole point of this exercise is to teach you how to think differently, teach you how to look at stuff that we normally don't see so that we can identify the full depth and richness of the problem spaces we're working with so that we can create solutions that solve for challenges in that problem. So that we can see what others cannot see, so that we can count what others cannot count. Hence, the nature of the assessment based on both counting, abstraction, pattern recognition, and logical thinking questions. All right. Oh, so there you go. There's the example. There's the example of how, opening up the board leads to a challenge. You opened up the board with basic, and surprise, surprise, the AI moves in for the kill with a score of 48. And there we go. This 48 is essentially the reason. So that's me. I just basically got my very large behind handed back to me on a platter. And this marks the end of all the questions in the question set variation VX that you took on Sunday. This also marks the end of the recorded part of the tutorial section. For those of you who can make it, I look forward to seeing you at 5:30 p.m. at Aman CD, MCS 5, where we will run a live session focused less on the questions that I have addressed and more on the questions that you have. Thank you very much for your time and patience. This is Jawad Ahmed Fareed signing off on behalf